Okay, so yeah, so we're gonna start with the class. Right, let me quickly screen share so that be on my screen. Let's see. Okay, let's share. Okay, can everyone see my screen? Can we all see my screen? I want to hope so. Okay, so these are the notes that I've sent to you. I've left them in Word because I do want to just edit here and there. I find that during the class that I do pick up things and stuff like that. Okay, so in the notes, you'll see that I start with an introduction session. So for those of you that are new here, I generally just give you tips on how to study, just the basic premise of what MTV is about and how we're converting hydraulic/pneumatic energy into mechanical energy, or vice versa, mechanical energy into hydraulic/pneumatic energy. And then just how to give some study tips over here, how to study MTV on your own. And then the main thing is you just have to do lots of questions. So what I'm going to aim to do is, because there's still about 2 days left before you write, after the class, I'm going to compile a list of problems that I recommend for semester test 1, divided into the sections. So all your STEAM fundamental questions that I recommend, all your axial flow turbine questions and all of that from all the past paper questions that are available. Another thing is there's this drive with, if you click on the link, you'll see it's going to take you to past paper drive section by section. So it will be all the past papers that are also divided based on the section of MTV. And it's also quite good. And then this is the general drive with the tables and everything. And then yeah, how to study MTV. And yeah, so that's just read through the introduction in the notes. It's quite good. And yeah, because I really want to get into this class. And yeah, guys, so we're looking at STEAM fundamentals, right? This is pretty much where we're going to start off. And STEAM fundamentals, you would recognize it's essentially your power or your STEAM power diagrams from your or from MTX 221. You recommend them, also MTX 311 somewhat, but you remember these from MTX 221. But in MTV, it's on another level. It's obviously going to be more difficult than MTX 221, right? And the idea with MTV 420 is we want to do TS diagrams. We want to create the TS diagrams for such steam cycles. Essentially a Rankine cycle or an advanced Rankine cycle, because the Rankine cycle consists of a boiler, your turbine, your process heater, your condenser, and then your pump, right? And then you got these new components like an expansion valve. You can just quickly look here at such as, here's another example. You also got a trap. You can have them divided into a high and low pressure turbine. There's a lot of different ways. There's a lot of different circuits, or a lot of different cycles you get. You also get ones. Let's just quickly look here. I just want to move my screen so you can see. I didn't put this question in there because I'm not going to cover it in today's class. But you also get ones with heat exchangers, and where you have essentially you have your steam power, which is now heat exchanger, which is going into another cycle, right? But this is from let's quickly check here. This was from assignment 1 2016. So this is one of those as well, but I'm not going to cover this one, right? Because obviously I need to cover axial flow and all sorts of other questions. So yeah, but I will explain to you the idea of what's going on here, but everything else pretty much remains the same. It's just the only tricky thing is just this heat exchanger. How do we deal with the heat exchanger, right? Okay, so let's get into the question. So okay, so I'm going to create I just have to quickly create a whiteboard. Okay, so I'm going to create a whiteboard, MTV 420, and then I can draw and do all sorts of stuff with the whiteboard. Okay, so this is where I will, okay, you can see me there. Video. Okay, whiteboard. Okay, guys, so yeah, so this is where I'll draw. It will be all interactive. Okay, so And I just hope everyone's got the notes and we can all see the notes from the class. Okay, so let's jump into it. Remember, if you guys have any questions, please do just pause me, and then I'll give an opportunity to speak, and then and then if I'll also be switching your mics off if I hear some background noise and you're not participating in just some noise, I'll also switch your mics off. Okay, so also please ask questions when you have an opportunity. Okay, so the main idea with these STEAM cycles or STEAM fundamentals is you want to draw your TS diagram. And what I outlay here is I outlay a framework for you to draw your TS diagrams, right? So when you're drawing a TS diagram, right, the first thing you want to do is you want to draw a table that looks like this. So you want to have your pressures, you want to have your temperatures, and then obviously you're going to list all your pressures that are equal to here, all your temperatures, your mass flow rates, because when the thing's split up like this, your mass flow rates are going to change, all your entropies and all your enthalpies. So this is what I used last year for the STEAM cycles, and it's a framework that it would always work for every STEAM cycle. Okay, let's just add him. Okay, so yeah. Okay, so there's basically a list of components that you get with the steam cycles. Is you get your boiler, as we're all familiar with. You get a condenser. You get your flow splits, like where they split. You get your process heater, which is essentially, it can also be considered like a condenser. So a process heater works like a condenser, but sometimes it doesn't work exactly like a condenser, where you can have pressure drop and so forth, but that depends on the question. But just note that you got a process heater. I'll just say similar to condenser. So it's similar to a condenser, right? Wait, condenser. And then you got a mixing chamber / feed water heater, and it's also it's okay. Well, it's known as a closed. So a mixing chamber is where they mix, right? So if you look here, well, there's no. If we quickly look at one of our questions here, actually, wait, I can even just scroll down in the notes and you'll see what I'm talking about. So a mixing chamber looks like, there's a mixing chamber there. So it's when all your fluids or your steam mixes inside the chamber, and then essentially it takes the high temperature, the low temperature, and then creates a new temperature here. But it's just note all the pressures are the same, but you'll see I have this little table that explains to you what the states are and all of that. Which you have to know that. There's no way around. You just have to understand that those are the states. But yeah, you have a mixing chamber, closed feed water heater, and then you have a heat exchanger. Right, you have a heat exchanger / what's also known as an open feed water heater. Right. So I will update the notes, the new notes. Okay, so so what you want to do is you want to first draw your table and list the pressures, the temperatures that's given to you in the question. Then you want to add the states. So at every point there's a state. So when you come out of the boiler, it's going to be it's going to be a superheated vapor, right, for the turbine. Then obviously when it comes out of the turbine, it's going to be a saturated vapor. Then you're going to have your process heater. So you basically just have to know the states. Like, coming out of the pump, it's going to be a compressed liquid. Going into the pump, it's going to be a saturated liquid. So I've listed here in the table, right, like at your boiler, the state going into the boiler is a compressed liquid. It's always a compressed liquid. Going out, it's always a superheated vapor, right? There's always constant pressure. There's you just have to know that the temperature out is always above the temperature in. The boiler is also known as a steam generator, right? So just take note of that. Then you have your turbine, right? You have your turbine, and then going into the turbine, it's always superheated vapor. Going out, saturated vapor. You have isentropic. Yeah, so it'll be isentropic. isentropic entropy. Yeah, so you always assume that there will be an isentropic state that you're going to use. You have your condenser. Your condenser state in is, so your condenser is this thing here, your process heater / your condenser, right? But just take note, like we're going to go through a question and I outline everything. I outline in here. Yeah, everything I outline here is pretty much the states that you just have to know. The mixing chambers, the heat exchangers, all of that. It's difficult to say the states because it really depends on the previous conditions. There isn't a defined state of what it's going to be going in, going out. But for your general components like your boiler / steam generator, your turbine, your condenser, your pump, all of that's pretty much defined going in and out. Okay, and usually for your states going out of your expansion valves and all of that, they're going to give you some sort of condition or some thermodynamic properties there that you can understand what the state is. Okay, so yeah, so we're just looking at how to draw a TS diagram, the framework, and then we'll actually do a question and we will see how to do it. Okay, so once you've listed all your pressures and your temperatures and your mass flow rates and your entropies and your enthalpies states, right? So for example, let's do an example breaking down this specific question here, right? So if we break down this question, we know that P7 is equals to P1, right? Because going through the boiler, it's always going to be constant pressure, right? And the most important part to draw a TS diagram is actually these pressures. You need to know your pressures. If you know the pressures, then it's quite easy, right? You know that pressure, or we know that P7 equals to P1, which is equals to pressure 2, which equals to pressure 3, right? Let's list it like that. Let's just move this. What? Just going to move this a bit so that I have more space for these pressures. Okay, so we have P7 equals to P1, which equals to P2, which equals to P3. Right, we know that through your process heater, the pressures are always constant, right? So P4 will equals to P5, which will equals to P6, right? And then, yeah, that's pretty much that. That's what we know, and we know then we have P7, which is by itself. We don't know. Oh no, that's actually basically it. Because yeah, that's basically it. And then we have that's actually basically it, right? So then we have our temperatures and our mass flow rates. So we have the general system will be mass flow rate M. In this case, we call it M, right? But then we're going to have, when it splits up here, we will have M2. And generally, it will be some kind of a percentage. They'll give you a percentage. They'll tell you that mass flow rate 1 or mass flow rate 2 is 20% of the mass flow rate, for example. This is just an example. Then you'll say that mass flow rate 2 is equal to 0.2 M, because you always need to get it in terms of M, right? So we got M, but this is just an example. Remember that it's not a general case. It's just assuming that mass flow rate 2 is 20% of mass flow rate M, right? So therefore, mass flow rate 3 will equal to 0.8 mass flow rate, right, to the system. So M is our mass flow rate of the system. Yeah, there we go. Then we have to look at our entropies, and generally S of S. Let's do this. So at state 3 for a turbine, because we're dealing with because MTV is dealing with or advanced thermodynamics, we never assume the turbine to be isentropic. It's always going to be some real process, and it always gives you isentropic efficiency. So they'll tell you that isentropic efficiency of the turbine NP. Let's insert an equation so it looks nice. Right, it will always tell you that NT is equals to just remember guys, I'm just making examples. It will be 0.9. But if nothing is stated at all regarding isotropic efficiencies, then assume that it's 0. Then just assume that it's 1. Okay, but I even tell you in these notes here, I say if isotropic efficiency of turbine and pump is not mentioned or given, you can assume it is 100%. So NP equals to 1, and NP of our turbine is also equal to 1. Okay, so we can assume this. All right. Okay, so let's quickly go back what we were doing. But this is if they give. I'm just assuming, let's say they give it to you as that. Right? Then, okay, so we know that we have that. We know that, wait, let me just copy this and that. So please also, like, for the specific example that I'm doing here, just explaining to you how you populate the table. Right, wait, let's go back. Then your NT, oh wait, I just want to do that. So then your state, this thing. Okay, your state. I don't want to. I want to draw the equation. No, it's fine. Okay, so your state. So what you have to know is state 3, right? State 3 will equal to S5 or S5, right? But only F5 of S. So it's only for the isentropic part, and then the same applies for the turbine, right? For the pump. So the pump, that will be state 6, and then it will be state 6 to 7S. So it's always gonna. So this is just, but yeah, this is going from for the pump 6 to 7, and then you have to know for an expansion valve, it's also known as a trap. An expansion valve is also known as a trap. That H2 is equal to H4. Equals to H4, right? H2 equals to H4, right? And generally, not always, but generally for a condenser, or you can assume that T4 is equals to T5, which equals to T6. It's just an assumption for now. Yeah, T5 or T5 equals to T6. Right, and the reason why we can assume that is because when you have a process heater, what does a process heater do? It converts this vapor that's coming out of here. It's a mixture between liquid and vapor. It converts this into a liquid so we can pump it, right? But if we doing that, we're going to be in the saturation region over here. And if we're in the saturation region, it means that the temperature over here remains constant. So if we here, but anyway, let's quickly. But this is just a general assumption. This would be for, this is just a general assumption. It's not always the case, but if it does lie in this region, if your state 5 was here, state 6, then it will be here. But as we can see, the pressure is the same, but the temperatures differ wildly for all of them. So actually, for this specific one, they're not the same. But this is if you had a condenser. But that's why I said for a process heater. Oh wow. Okay, so I've got 10 more minutes, and then we'll start a new Zoom call. Apparently, you can't do a long call. Okay. Okay, so yeah. Okay, so let's quickly do that. So you do your table for your pressures, your temperatures, your mass flow rates, your entropies, everything you know about the entropies, and then your enthalpies that you know from the diagram, like just by observation that you know. Okay. Then what we do is, so we say list all component inlet and outlet pressures that are equal to one another and add to the table. So what you want to do is yeah, you want to add all the pressures as we just did, the temperatures, everything that you know. Then what you want to do is you need to know the states. you need at each stage you need to know the state. Like, is it a liquid? Is it a saturated liquid? What is it? And as I've already given you the breakdown of what it is at each state for each one, you just need to know that. Alright, so I've broken it down here for you guys. I've already told you what that is. Right, but and yeah, so then once we know the states and we have our table as we see here, then it's very easy to draw our TS diagram. So then yeah, draw the TS diagram. I recommend you draw it with pencil, right? Then add the pressures to the TS diagram in the saturation region. So you see the pressures are always added in the saturation region, like on the lines. That's what we do there. And then and then draw the power cycle, the direction it flows like that. And then yeah, so when you start drawing the power cycle, you always want to start with the pump inlet stage, which is in this case here at number 6. You're always going to start here at number 6. The reason being is because we know it's always going to be a saturated liquid here. And a saturated liquid just means that it sits on this line. It's over there, saturated liquid. It sits there. Over here at this line, a saturated vapor. So we sit there, quality is equal to 0. And then obviously when you pump it, it's going to go up like that. You're going to increase the pressure of the fluid. Okay, so you start at the pump stage and then add mass flow rate to the TS diagram. You can add mass flow rates. Yeah, add mass flow rate. So you see, generally it's not here, but generally we add the mass flow rate. If the mass flow rate does split up, then you just add the mass flow rates to the system. Okay, but this is just an explanation. Let's actually do a question together. Okay, so yeah, so then also just take note of the assumptions. You have an adiabatic turbine, pump, mixing chamber. So adiabatic turbine, pump, mixing chamber, flow lines. This should be flow lines, which basically means QZ, your heat loss is equal to 0. Right, so I don't know what's going on here. Oh, yeah, and then another assumption is that there's no pressure losses. There's no pressure losses over the flow lines. Over flow lines, steady state. Yeah, and that's pretty much our assumptions there. And then we have our table with all our equations. So generally, with all the equations, you're just going to be using energy conservation around the components. And then you want to find your enthalpies, and your enthalpies, you use your tables. So in your tables, that's going to be your, wait, let's see, wait, I guess it's not working here. But in your tables, in your tables, that's going to be, word, so annoying. Okay, so in your tables that you're going to use your saturated tables, your saturated water tables, right? And saturated just means that if something saturated lies in this region here, right? So you have your saturated water tables, right? And then you have your superheated steam tables, and then a new one which we never experienced in your in MTX221 is a Mullet diagram. And a Mullet diagram, it's the best thing. I highly recommend you use this. Use this first. Or actually, wait. So what you do is you can use the Mullet diagram. If you see that, use if you have to linear interpolate. If you have to linear interpolate the steam tables. So basically, with steam tables, the linear interpolation can be quite cumbersome. So instead of just doing that and having to linear interpolate, you can just use the Mullet diagram, and it's much quicker. Yeah, much quicker, right? And then you also got cycle efficiency, which is your turbine efficiency minus the work boiler. And now this is just basically your formulas that you need to know. your formulas for your boiler. It's also known as a steam generator. This is your this is this wait, this is supposed to be M here. This is your boiler steam generator. This is your turbine equations here. The main idea is with your turbine equations, this is a very important equation here that can allow you to find your enthalpies around a turbine in, out, right? Then you got your isentropic outlet state, right? And then this is also another, so this is basically the equation, because generally they want you to find this, you need to get this enthalpy out. They're never going to give it to you. So then what you do is you just use, so what you do is, let's quickly see. So what you do is you just use this equation here to do that, and that's your isotropic efficiency, HN. I mean, it's all there. It's all explained there. And how I get this equation here is just literally just from this equation there. Oh no, that's for a pump. But it's the same thing. This thing, which is equal to this thing here. Okay. So then what we do now is, I see here I said this was supposed to be pump. Alright, just fix this. I see that there's an issue there. Right, pump. Okay, so what we do now is we got a turbine, then the condenser is very simple equations. It's just this. That's all you can pretty much do for the condenser. Just note the constant properties here, and then that Tn equals to T out in the condenser, because it's in the saturation region, right? Isotropic efficiency. You have your pump conditions. The only thing you really need to take note of with a pump is this formula. This formula is one of the hack formulas of MTV. This formula here. Specific value N is equal to PR minus Pn plus Hn. And where we get that formula is, if you look at our diagram here, your so this, because you generally want to know what this, you want to know one of the enthalpies. You either want to know this enthalpy or generally this enthalpy, you want to know what this enthalpy going out is. And to get the enthalpy going out, right, what we do is, let's quickly, to get the enthalpy going out, all that we do is we use, we essentially just use this formula here. This is the hack formula going out of the pump. It's a very, very important formula. I can't emphasize this formula enough. And how we get the formula is just from this equation here. It's essentially just this. Right, and so these are just, I've already written them down. These are all your standard equations, right? And you need to use all these equations to get your, so there's 1 minute left, and then I must restart the call because Zoom, that's how it is, and then we'll start again. But so just take note, like we're looking to the mixing chamber stuff and all of that, and how that works, and the valves. But the only thing you have to know is with the expansion valve is that Hn equals to H out, the enthalpies and the pressures, and then that's pretty much it. And then we have our Mullet diagram, which looks like this. You have pressure lines, temperature lines. You have your enthalpy. I think it looks a little confusing. Okay, let's start a new meeting. Stupid Zoom thing.